The Continental R-nine 75 radial engine sat disassembled across 3 steel workbenches at Kumisdorf proving ground, its components laid out with surgical precision. German engineers circled the tables like doctors around an impossible patient, measuring tolerances, photographing surfaces, documenting wear patterns that contradicted every assumption they held about engine longevity. This American power plant, extracted from the captured Sherman tank designated Beutefahrzeug 259, had operated for over 4,800 kilometers across North African desert and German test courses without requiring anything beyond routine oil changes and basic filter maintenance. The mathematics simply didn't reconcile with German engineering experience, where tank engines demanded comprehensive overhauls every 800 to 1,000 kilometers just to maintain basic functionality. Senior engineer Klaus Hoffmann ran his calibrated measuring tools across the cylinder. Walls for the 3rd time that morning, convinced his initial readings contained errors. The bore measurements showed wear within acceptable tolerances. Surface finish still exhibiting cross-hatch patterns from original manufacturing. Piston ring seating marks indicating proper combustion chamber sealing throughout the engine's operational life. He had expected to find scored cylinders, worn bearing surfaces, degraded valve seats, all the typical indicators of an engine approaching failure after extended service. Instead, he documented an engine that appeared capable of thousands of additional kilometers without intervention. His colleague Werner Schmidt examined the valve train components spread across the adjacent bench, measuring valve stem clearances, checking spring tensions, inspecting rocker arm bearing surfaces for signs of inadequate lubrication or excessive loading. Every measurement fell within specifications that would be considered acceptable for a freshly rebuilt engine, not one that had endured months of combat operations followed by systematic German testing designed to stress every mechanical system to its limits. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Continental R-nine 75 represented American aviation engine technology adapted for armored vehicle use, a 9-cylinder radial design producing 400 horsepower at 2,400 revolutions per minute. German engineers recognized the basic architecture immediately, as radial engines were common in aircraft applications across all nations. What they couldn't immediately comprehend was how this particular design achieved such extraordinary durability under operating conditions that would destroy comparable German engines within a fraction of the operational lifespan. The testing data accumulated over 6 months told a story that challenged fundamental German assumptions about the relationship between engine performance, service life, and maintenance requirements. War Daddy 2 had arrived at Kumisdorf in spring of 1943 after its capture at Sidi Bouzid. German test drivers had immediately begun systematic evaluation trials designed to document every aspect of the tank's performance envelope and identify weaknesses that could be exploited in combat. The initial road marches across varied terrain logged over 350 kilometers before the tank even reached the proving ground, a journey that German tankers had expected would reveal mechanical problems requiring attention. The Sherman arrived at the test facility showing no signs of distress, its engine running smoothly, transmission shifting cleanly, all systems functioning within normal parameters. Test engineers developed comprehensive protocols to examine every aspect of the power plant's design and operation, beginning with non-destructive testing, while the engine remained installed in the vehicle. They measured oil consumption rates across different operating conditions, finding that the Continental burned less than 1 liter per 100 kilometers during normal operations, substantially better than German tank engines that often consumed 3 to 5 liters over the same distance. They monitored coolant temperatures during extended high-load operations, documenting thermal management that kept cylinder head temperatures within acceptable ranges, even during sustained maximum power output that would cause German engines to overheat within minutes. The air cooling system demonstrated elegant simplicity that contradicted German preference for liquid cooling in tank applications. The radial configuration positioned cylinders in a circular arrangement around the crankshaft, each cylinder head exposed to cooling airflow directed by a large fan driven directly from the engine crankshaft. German engineers had dismissed air cooling as inadequate for sustained high-power tank operations, believing that only liquid cooling systems could manage the thermal loads imposed by combat conditions. The Sherman's engine proved this assumption wrong through consistent performance that showed no tendency toward overheating, even during trials specifically designed to stress the cooling system. Test drivers pushed the tank up steep grades in low gear, forcing the engine to maximum continuous power output, while cooling airflow remained minimal due to low vehicle speed. German engines subjected to similar testing invariably overheated within 10 to 15 minutes, requiring shutdown and cooling periods before operations could resume. The Continental maintained acceptable temperatures indefinitely, its cooling system adequately designed with sufficient margin to handle worst-case scenarios that designers had anticipated during development. Engineers documented the oil system architecture with particular interest, recognizing design, elements that explained the engine's remarkable tolerance for sustained high-load operations. The lubrication system employed a full-flow oil filter positioned in the main pressure line, ensuring that every drop of oil circulating through the engine passed through filtration media before reaching critical bearing surfaces. German tank engines typically used bypass filtration that cleaned only a portion of the oil flow, accepting that some percentage of unfiltered oil would reach bearings, gradually accumulating contaminants that caused premature wear. The American approach reflected absolute commitment to component longevity, even if it required slightly more complex oil system plumbing and added the weight of a larger filter assembly. The oil pump itself demonstrated generous capacity margins, capable of maintaining adequate pressure across a wide range of operating conditions and engine speeds. German designers calculated oil pump capacity to meet minimum requirements with small safety factors, accepting that oil pressure might drop below optimal levels during extreme maneuvers or when engines wore beyond factory specifications. American engineers designed the oil system to maintain proper pressure even when engines accumulated substantial wear, ensuring adequate lubrication throughout the power plant's entire service life, rather than just during the first few hundred hours of operation. The crankshaft examination revealed manufacturing quality that impressed even skeptical German metallurgists who had expected to find crude American mass production techniques. The forged steel crankshaft showed precise journal dimensions, smooth surface finishes, and properly radiused fillets at all stress concentration points. German engineers had assumed that American mass production methods sacrificed precision and quality in favor of manufacturing speed and quantity, believing that only German craftsmanship and attention to detail could produce truly reliable engine components. The Continental crankshaft disproved this prejudice through physical evidence that American manufacturing could deliver both quantity and quality simultaneously when proper industrial processes were implemented at scale. The connecting rods displayed similar manufacturing excellence, each one precisely matched in weight to minimize vibration and bearing loads. German practice involved weighing connecting rods and grouping them by weight class, accepting small variations between individual components as inevitable in mass production. The American rods showed weight variations of less than 5 grams across the entire set of 9, indicating manufacturing control and quality standards that German factories achieved only through extensive hand finishing and selective assembly. The piston and ring package demonstrated design philosophy differences that explained much about comparative engine longevity. Each piston carried 4 rings, 3 compression rings to seal combustion, pressure, and 1 oil control ring to manage cylinder wall lubrication. German practice typically employed 2 compression rings and 1 oil ring, accepting higher oil consumption and blow-by in exchange for reduced friction and simplified manufacturing. The American design prioritized complete combustion sealing and precise oil control, even though it required more complex ring manufacturing and slightly increased friction losses. The trade-off proved worthwhile in extended service, as the additional rings maintained effective sealing throughout the engine's operational life, while German engines with fewer rings experienced steadily degrading compression and increasing oil consumption as components wore. The oil control rings specifically impressed German engineers examining them under magnification, as the multi-piece design with expander springs maintained consistent cylinder wall contact pressure throughout the piston's stroke. This ensured proper oil film thickness under all operating conditions, preventing both oil starvation that would cause scuffing and excessive oil that would burn in the combustion chamber. The valve train architecture reflected aircraft engine heritage adapted successfully to ground vehicle requirements. The overhead valve configuration employed push rods and rocker arms to actuate valves positioned above each cylinder, a layout that provided excellent breathing characteristics and efficient combustion chamber design. German tank engines typically used side valve configurations that were simpler to manufacture and maintain, but provided inferior breathing and lower specific power output. The American willingness to accept slightly more complex valve train mechanisms in exchange for better performance and efficiency demonstrated confidence in their manufacturing capability and design validation processes. Each valve spring showed minimal loss of tension after thousands of kilometers of operation, indicating proper material selection, and heat treatment that maintained spring characteristics throughout extended service. German valve springs often required replacement during engine overhauls due to tension loss that could allow valves to float at high engine speeds, potentially causing catastrophic contact between valves and pistons. The Continental valve springs showed no signs of such degradation, suggesting service life potentially exceeding 10,000 kilometers under normal operating conditions. The carburetor system employed a relatively simple design that contradicted German assumptions about the complexity required for reliable engine operation across varying conditions. German tank engines used sophisticated carburetor designs with multiple jets, accelerator pumps, and enrichment circuits intended to optimize fuel delivery across the entire operating range. These systems worked well when properly maintained by skilled technicians who understood their adjustment procedures, but they required frequent attention and precise calibration to maintain optimal performance. The Continental used a simpler carburetor design with fewer adjustable elements, accepting slightly less precise mixture control in exchange for reliability and ease of maintenance by mechanics with basic training. The American philosophy prioritized keeping engines running adequately, rather than achieving theoretical optimization that required constant expert adjustment. Field maintenance personnel could service the Sherman's carburetor with basic tools and minimal specialized knowledge, while German carburetors demanded specialized gauges, precise adjustment procedures, and thorough understanding of their operating principles. The ignition system demonstrated similar design philosophy, favoring robust simplicity over theoretical sophistication. The magneto-based ignition eliminated dependence on battery power, ensuring that the engine could start and run even if electrical system failures occurred elsewhere in the vehicle. German tanks used battery-powered ignition systems that provided excellent performance under normal conditions, but could fail completely if electrical problems developed, leaving the vehicle immobilized until repairs were completed. The Continental's magneto continued generating spark as long as the engine turned, providing inherent redundancy that eliminated single-point failure modes in the ignition system. The spark plug examination showed minimal electrode wear despite extended service, indicating proper combustion chamber conditions and adequate cooling that prevented plug overheating. German engines often experienced spark plug fouling from oil consumption or plug failure from excessive temperatures, requiring frequent plug changes to maintain reliable ignition. The Continental's plugs appeared capable of extended service without replacement, another indicator of design margins that exceeded immediate requirements. Engineers measured bearing clearances throughout the engine, documenting wear patterns that provided insight into lubrication, effectiveness, and load distribution across all bearing surfaces. The main bearings, supporting the crankshaft, showed uniform wear patterns indicating proper oil supply and loading, with clearances that had opened only slightly beyond factory specifications despite thousands of kilometers of operation. German engines typically showed much more rapid bearing wear, particularly in high-load applications like tank service, where continuous high-power operation imposed severe demands on bearing materials and lubrication systems. The connecting rod bearings displayed similar wear characteristics, with clearances remaining within acceptable limits and bearing surfaces showing no signs of scoring, galling, or oil starvation that would indicate lubrication inadequacy or excessive loading beyond design capacity. The cam followers and rocker arm bearings showed minimal wear despite the constant reciprocating loads imposed by valve train operation. German engineers recognized that these components typically wore rapidly in their own engines, requiring replacement during overhauls to prevent valve train problems that would degrade engine performance and potentially cause catastrophic failures if neglected. The metallurgical analysis of key components revealed material quality that matched or exceeded German military specifications, despite American mass production methods. Test samples extracted from the crankshaft showed uniform grain structure and proper heat treatment throughout the component, indicating quality control processes that ensured consistent material properties across production runs, numbering in the thousands. German procurement of engine components involved extensive incoming inspection and testing to verify that suppliers met specifications, as quality variations between manufacturers and even between production batches from the same supplier were common enough to cause concern. The American materials showed remarkable consistency, suggesting that quality control was built into the manufacturing process rather than being verified through post-production inspection and testing. The cylinder barrel material demonstrated excellent wear resistance despite extended service under conditions that included North African sand ingestion and sustained high-power operation during German testing. Microscopic examination of cylinder wall surfaces showed wear patterns consistent with proper lubrication and minimal abrasive contamination, contradicting German assumptions that American air filtration would prove inadequate for desert conditions where fine sand could destroy engines within hundreds of kilometers if filtration was insufficient. The engine's overall condition after comprehensive teardown and inspection forced German engineers to confront uncomfortable conclusions about their own design priorities and manufacturing capabilities. This American engine had operated reliably for distances that would require 2 complete overhauls of comparable German power plants, yet showed wear patterns, suggesting it could continue operating for thousands of additional kilometers before requiring major maintenance intervention. The design incorporated no exotic materials or revolutionary technologies that German engineers couldn't understand or replicate given adequate resources and manufacturing capacity. What the Continental demonstrated was something more fundamental and more difficult to copy than any specific technical innovation. It represented decades of American automotive industry experience, translated into military applications, embodying design philosophy that prioritized practical field reliability over theoretical performance optimization, generous margins over minimum adequate specifications, and ease of maintenance over complexity that required specialized knowledge. German tank engine development had followed different priorities, emphasizing maximum performance from minimum displacement, sophisticated systems that required expert maintenance, and designs that assumed highly trained personnel would be available throughout the vehicle's service life. These philosophical differences produced measurable results that became impossible to ignore as testing data accumulated through summer and autumn of 1943. The Continental R-nine 75 required oil changes every 500 kilometers and basic filter maintenance at similar intervals, with no other routine service needed between major overhauls projected at 5,000 kilometers or more. German engines demanded oil changes every 250 kilometers, frequent valve adjustments to maintain proper clearances, regular carburetor recalibration to maintain proper mixture settings, and comprehensive overhauls every 800 to 1,000 kilometers just to maintain basic operational capability. The maintenance burden difference meant that Sherman tanks could spend more time in combat operations and less time in maintenance facilities, while German tanks required constant attention from skilled mechanics, who were increasingly scarce as the war continued, and trained personnel were consumed by combat losses or reassigned to address shortages elsewhere. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The testing program expanded to include destructive testing, designed to identify failure modes and establish ultimate performance limits beyond normal operating parameters. Engineers ran the engine at maximum power output continuously for extended periods, monitoring temperatures, oil pressure, and vibration characteristics, while documenting how long the engine could sustain abuse that far exceeded any realistic combat scenario. German engines tested under similar protocols typically failed within 30 to 60 minutes, suffering bearing failures, valve problems, or cooling system inadequacy that caused catastrophic damage, requiring complete rebuilds. The Continental ran for over 8 hours at maximum continuous power before test engineers finally shut it down, not because the engine showed signs of distress, but because they had accumulated sufficient data to document its remarkable durability under extreme conditions. Post-test inspection revealed that the engine had survived this abuse with no permanent damage, requiring only fresh oil and a cooling period before it could return to normal service. German engineers documented this result with mixture of professional admiration and personal frustration, recognizing that American designers had achieved something German industry had never accomplished despite theoretical knowledge that should have enabled similar performance. The implications extended far beyond simple mechanical comparisons between individual engines to fundamental questions about industrial capability and design philosophy that determined military effectiveness. Germany had entered the war with confidence in its technical superiority and engineering excellence, believing that superior design and scientific knowledge would overcome any material disadvantages or numerical inferiority against less sophisticated opponents. The Sherman engine testing revealed that this confidence had been misplaced, based on assumptions about American industrial capability that proved completely wrong when confronted with physical evidence. American automotive industry had developed manufacturing processes, quality control systems, and design principles through decades of commercial competition in civilian markets, where reliability and cost-effectiveness determined success or failure. These mature industrial capabilities translated directly into military production once the United States entered the war, enabling American factories to produce weapons that worked reliably in field service. Despite being designed and manufactured at scales, German industry never approached. The Continental engine represented this industrial maturity, made tangible, a component that performed exactly as its designers intended throughout its service life, because American engineers understood how to design for reliability, and American manufacturing could execute those designs consistently across production runs numbering in the tens of thousands. German industry lacked this foundation of mature mass production experience, having never developed civilian automotive sector at comparable scale before the war. German tank engines reflected this limitation through designs that prioritized performance specifications over reliability, sophisticated systems over robust simplicity, and theoretical optimization over practical field maintainability. These choices made sense within German industrial context, where production runs were measured in hundreds or low thousands, rather than tens, thousands, where skilled craftsmen were available to hand-fit components and adjust systems to achieve proper operation, and where designers assumed that military vehicles would receive expert maintenance throughout their service lives. American industry operated under completely different assumptions that shaped every design decision in ways that proved far more appropriate for sustained military operations under field conditions. The Sherman engine could be maintained by mechanics with basic automotive training using common tools and readily available spare parts. It tolerated operational abuse that would destroy more sophisticated engines designed to narrower margins, and it delivered consistent performance throughout extended service life that made logistical planning possible and operational readiness predictable. The engine reassembly at Kumisdorf proceeded with meticulous care. Each component returned to its precise position as German engineers photographed every step for technical documentation that would circulate through Wehrmacht engineering departments and armaments ministry offices. The process took 3 full days, despite the engine's relatively straightforward design, not because of complexity, but because the engineers wanted to understand every detail of how American designers had achieved such remarkable durability through seemingly conventional components arranged in familiar configurations. The answer emerged gradually through careful observation and measurement. Excellence resided not in revolutionary innovations, but in countless small design decisions that individually seemed unremarkable, yet collectively produced extraordinary reliability. Every bearing clearance specified with adequate margin rather than minimum acceptable tolerance, every oil passage sized generously rather than calculated to theoretical minimums, every component designed to survive abuse rather than merely handle expected loads. American engineers had built an engine that assumed field conditions would be harsh, maintenance would be imperfect, and operators would occasionally make mistakes, then designed every system to function adequately despite these realities, rather than requiring ideal conditions that rarely existed in combat. Werner Schmidt drafted the initial technical report summarizing findings from the Continental engine examination, choosing his words carefully to convey the significance of what they had discovered without appearing defeatist or undermining confidence in German engineering capability. The report noted that American automotive industry had demonstrated manufacturing maturity and quality control processes that enabled reliable mass production of complex mechanical systems at scales. German industry could not currently match. It documented specific design features that contributed to the engine's exceptional durability, including the full-flow oil filtration system, generous bearing clearances, robust valve train, components, and effective air cooling system that maintained proper temperatures under sustained high-load operations. The report avoided explicit comparisons with German tank engines, though readers familiar with Maybach and other German power plants would immediately recognize the implicit contrasts between American design philosophy, emphasizing reliability, and German approaches, prioritizing maximum performance from minimum displacement. Schmidt concluded with observations about maintenance requirements, noting that the Continental demanded far less frequent service than comparable German engines and could be maintained by personnel with basic automotive training rather than requiring specialized knowledge and extensive technical education. The report circulated through Wehrmacht technical branches during autumn of 1943, reaching offices where senior engineers and procurement officials struggled with increasingly desperate situations as German tank production failed to meet requirements, and field units reported catastrophic mechanical reliability problems across all vehicle types. The Sherman engine analysis arrived at a moment when Germany's industrial limitations had become impossible to deny. Even to optimists who had believed superior German engineering could overcome material disadvantages and numerical inferiority. Panther tanks were suffering final drive failures that immobilized vehicles after barely 100 kilometers of operation. Tiger tanks demanded maintenance halts every 50 kilometers during road marches, and even the reliable Panzer IV was experiencing declining quality as manufacturing standards degraded under pressure to increase production rates, while skilled workers were conscripted for military service and replaced with slave labor that had no incentive to maintain quality standards. The Continental report documented an enemy power plant that simply worked without the constant crises that plagued German armored forces, providing tangible evidence that American industrial capability exceeded German assumptions by substantial margins that could not be explained away through propaganda or wishful thinking. Additional captured Sherman tanks arrived at Kumisdorf through 1944 as Wehrmacht forces retreated across multiple fronts, and increasing numbers of American vehicles fell into German hands either through battlefield capture or recovery from abandoned positions. Each captured tank underwent systematic examination, with engineers paying particular attention to engines that had accumulated substantial operational hours before capture. The pattern held consistent across every vehicle examined. Continental engines showed wear patterns indicating extended service life potential, maintained proper oil pressure and compression even after thousands of kilometers of operation, and demonstrated tolerance for harsh conditions that would destroy German engines within fractions of the operational lifespan American power plants routinely achieved. The consistency across multiple captured vehicles from different production batches and time periods proved that the reliability wasn't accidental or limited to particularly well-built examples, but represented standard manufacturing quality that American industry delivered routinely across production runs, numbering in the tens of thousands. German engineers recognized that they were not examining exceptional vehicles that happened to be built particularly well, but rather typical examples of what American factories produced every single day in quantities that dwarfed German output of all tank types combined. The diesel-powered Sherman variants captured from Soviet forces on the Eastern Front provided additional insights into American automotive versatility and manufacturing flexibility. The M4A2 employed twin General Motors 6046 diesel engines that delivered performance comparable to the gasoline-powered Continental while consuming substantially less fuel and offering reduced fire risk from fuel system damage. German engineers had experimented with diesel tank engines during the 1930s, but abandoned development due to manufacturing difficulties, with fuel injection systems and the complexity of compression ignition technology applied to military vehicles. American industry produced diesel Shermans alongside gasoline variants without disrupting production schedules or requiring separate manufacturing facilities, demonstrating industrial capability to manufacture complex power plants in multiple configurations while maintaining quality standards across all variants. The General Motors diesel showed the same robust reliability as the Continental radial engine, with generous design margins, effective lubrication systems, and tolerance for operational conditions that would challenge more sophisticated engines designed to tighter specifications. Test engineers documented that the diesel variant actually exceeded gasoline Sherman reliability in several metrics, particularly in sustained high-load operations, where diesel fuel's higher energy density and compression ignition's thermal efficiency provided measurable advantages in specific fuel consumption and operational range. Field reports from German units employing captured Shermans reinforced the Kumisdorf testing data with real-world operational experience under combat conditions. German mechanized formations, desperate for reliable vehicles, as their own equipment degraded enthusiastically, incorporated any captured American tanks they could obtain in serviceable condition. Unlike Soviet 34 tanks, which Germans extensively modified before placing in service, Shermans entered German formations without significant changes because they functioned properly as designed, with no fundamental flaws requiring correction. German crews praised the Sherman's automotive reliability in letters home, in official reports, to higher commands, and in post-war interviews conducted by Allied intelligence organizations seeking to understand German perspectives on Allied equipment. Panzer troops, who had experienced multiple mechanical failures in Panthers and Tigers, found the Sherman's consistent reliability remarkable enough to comment on it repeatedly, noting that they could focus on tactical considerations rather than constantly worrying whether their vehicle would complete missions before mechanical failure left them stranded in hostile territory. The human dimension of this reliability gap emerged most clearly in individual soldier accounts that documented how mechanical unreliability affected tactical decisions and combat effectiveness. German tank commanders learned to plan operations around expected mechanical failure rates, calculating that substantial percentages of their vehicles would break down before reaching combat zones, and additional failures would occur during actual fighting. American tank commanders could reasonably expect that vehicles departing maintenance facilities would reach their objectives and complete assigned missions, barring combat damage or catastrophic mechanical failures that occurred at predictable low rates. This difference in operational planning fundamentally shaped what each force could attempt tactically, with American units able to conduct sustained operations over extended periods, while German formations had to carefully husband their limited operational vehicles and accept that mechanical attrition would eliminate substantial combat. Power before enemy action destroyed a single tank. The Sherman's reliability didn't make it invulnerable to German anti-tank weapons or immune to the tactical challenges American armored forces faced against dug-in German defenders, but it ensured that American tanks reached the battlefield ready to fight, rather than being abandoned along approach routes due to mechanical failures that should never have occurred in properly designed equipment. By early 1945, as Soviet forces approached Berlin from the east and American and British forces advanced from the west, the lessons from Kumisdorf testing had been thoroughly validated through 3 years of combat experience across multiple theaters. German tank production had collapsed under combined effects of strategic bombing, raw material shortages, and transportation system disruption that prevented components from reaching assembly facilities even when manufacturing capacity existed. The tanks Germany did manage to produce suffered from declining quality as slave labor replaced skilled workers, and desperate measures to increase production rates eliminated quality control steps that had previously caught defective components before they reached field units. Meanwhile, American Sherman production continued at steady rates from factories safely distant from any combat zone, staffed by motivated workers earning good wages under decent conditions, supplied with unlimited raw materials from sources Germany could not threaten, and supported by transportation infrastructure that efficiently moved components and completed vehicles to ports for shipment overseas. The industrial comparison that had seemed perhaps manageable in 1943 had become absolutely hopeless by war's end. With American productive capacity so far exceeding German capabilities that no amount of technical sophistication or tactical skill could compensate for the fundamental disparity in resources and manufacturing maturity. The final Kumisdorf reports, prepared before the facility's evacuation ahead of Soviet advances, documented observations about why German tank development had failed to match American automotive reliability despite theoretical knowledge that should have enabled comparable performance. The analysis identified institutional and cultural factors rather than technical ignorance as the primary obstacles to achieving American-style reliability in German designs. German engineering culture emphasized theoretical optimization and sophisticated solutions to technical challenges, approaching design problems with scientific rigor that sought mathematically optimal answers to complex questions. This approach produced impressive technical specifications and vehicles that looked formidable on paper, but it consistently undervalued practical considerations like ease of manufacturing, simplicity of maintenance, and tolerance for imperfect operating conditions. American engineering culture, shaped by decades of commercial automotive competition, emphasized practical solutions that worked reliably under real-world conditions, even if they sacrificed theoretical performance or employed less elegant technical approaches. American engineers designed for manufacturing reality rather than theoretical ideals, accepting that production workers would have varying skill levels, that field maintenance would be performed by mechanics with limited training, and that combat conditions would subject equipment to abuse far exceeding normal operating parameters. The Continental engine and the broader Sherman design philosophy it represented had emerged from this pragmatic American engineering approach that German culture found difficult to embrace, even when confronted with evidence of its effectiveness. German engineers could disassemble the Continental, measure every dimension, analyze every design feature, and understand intellectually why it worked so well, yet they struggled to apply those lessons to their own designs because doing so required abandoning assumptions that ran deep in German technical education and industrial practice. The belief that precision manufacturing and tight tolerances produced superior equipment, the assumption that sophisticated designs demonstrated engineering excellence, the conviction that theoretical optimization should guide design decisions, these principles seemed self-evidently correct within German engineering culture, even though combat experience and captured equipment testing proved they produced inferior results compared to American approaches, emphasizing robust simplicity and generous design margins. The institutional resistance to learning from American methods persisted even as German tank reliability remained catastrophically poor, and field commanders begged for vehicles that would simply work without constant mechanical crises. The post-war fate of German tank engineers and designers illustrated how thoroughly the lessons of reliability had been absorbed, at least by those who survived to apply them. When West Germany began developing the Leopard 1 main battle tank during the 1950s, the design team included veterans from wartime tank development programs who had studied captured Allied equipment and read the Kumisdorf reports documenting American automotive excellence. The Leopard 1 incorporated design philosophies that would have seemed alien to German engineers in 1943, but had become accepted wisdom after defeat, taught humility, and forced recognition that German approaches had been fundamentally flawed. The new tank emphasized reliability and maintainability over maximum theoretical performance, employed automotive components designed with generous margins rather than calculated to minimum specifications, and prioritized ease of field maintenance, using common tools rather than requiring specialized equipment and extensive technical knowledge. The Leopard 1 became one of the Cold War era's most successful tank designs, serving with numerous armies and remaining in production for decades. Vindication for the lessons that had been so painfully learned through testing captured Shermans while Germany lost the war. The mathematics of armoured warfare that had been rewritten at Kumisdorf during 1943 proved more enduring than the specific vehicles that illustrated those principles. The Sherman tank was obsolete within years of World War II's end, outclassed by new designs that incorporated lessons learned during the conflict and applied advancing technology to armoured vehicle development. But the fundamental truth, that reliability determined tactical effectiveness more surely than firepower or armour protection, remained valid across subsequent decades of tank evolution. A tank that reached the battlefield and functioned when needed was always more valuable than a theoretically superior vehicle that broke down before engaging the enemy or spent more time in maintenance than in combat operations. This principle, so thoroughly documented through Continental engine testing and Sherman operational experience, shaped tank development programs across all nations that studied World War II's lessons seriously. The countries that absorbed this wisdom produced successful armoured forces built around reliable vehicles that could be maintained by ordinary soldiers using standard tools. The countries that continued prioritizing impressive specifications over practical reliability repeated Germany's mistakes and suffered similar consequences when their sophisticated vehicles proved unable to maintain operational readiness rates adequate for sustained combat operations. The Continental R-nine 75 engine, that single power plant so meticulously examined at Kumisdorf, represented something larger than just excellent mechanical engineering or mature manufacturing processes. It embodied an entire national industrial capability developed over decades of commercial competition, shaped by democratic values that emphasized practical utility over impressive appearances, and refined through constant feedback between designers, manufacturers, and users operating in competitive markets where failure meant bankruptcy rather than requiring government subsidies to continue operations. German industry had developed under different conditions that emphasized state direction, prioritized military applications, and allowed inefficient practices to continue because they served political purposes even when they produced inferior economic results. These fundamental structural differences shaped what each industrial system could produce when mobilized for total war, with American decentralized capitalism proving far more effective at generating useful military equipment in overwhelming quantities than German state-directed economy that looked impressive in propaganda but consistently failed to deliver results matching its promises. The human cost of German engineering failure extended far beyond mechanical statistics or production numbers to real soldiers who died because their equipment failed when they needed it most. Tank crews abandoned in hostile territory when final drives broke, infantry units left without armoured support when Panthers couldn't complete approach marches, entire operations cancelled because insufficient vehicles remained operational to execute planned attacks. These consequences flowed directly from design decisions that prioritized specifications over reliability and manufacturing choices that sacrificed quality for quantity that still fell short of requirements. Every German soldier who fought in a Panther that broke down faced increased danger because his vehicle couldn't be relied upon. Every tank commander who planned operations around expected mechanical failure rates accepted casualties that resulted from equipment inadequacy. Every family that received notification of a son or husband killed in action paid the ultimate price for institutional failures that began in engineering offices and factory floors years before their loved ones entered combat. The Sherman's reliability advantage wasn't just a technical achievement or industrial triumph. It was a moral difference that saved Allied lives and cost German lives through the simple reality that American tanks worked when needed, while German, tanks too often did not. The final lesson from Kumisdorf transcended mechanical engineering or industrial economics to address fundamental questions about how societies organized themselves for conflict and what values guided their decisions under pressure. Germany had chosen to emphasize theoretical excellence, sophisticated technology, and impressive specifications that looked good in propaganda, but failed in practice because the underlying assumptions proved wrong. America had chosen to emphasize practical reliability, simple designs that ordinary people could operate and maintain, and adequate performance that could be sustained, rather than maximum capabilities that degraded rapidly under field conditions. These choices reflected deeper cultural values about the relationship between technology and humanity. Whether machines should be designed for idealized conditions or real-world messiness, and whether excellence meant impressing experts or serving users effectively. The Sherman, engine tested at Kumisdorf, delivered a verdict on these questions that no amount of propaganda could overturn or ideological commitment could deny, proving through physical evidence and operational experience that American values and approaches produced superior results when tested by the ultimate arbiter of total war. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.